Evening and welcome to a new food4Rhino webinar. Today we will learn about Flow. This is a new grasshopper plugin developed by Gianluca Casalnuovo that can help you simulate the movement of people in various scenarios, from routine pedestrian flow to emergency evacuations, while providing real-time feedback and optimization. Gianluca will show us today this plugin with first with a brief presentation, then with a live demo, and at the end, during the last 15-20 minutes, there will be time for questions. Please remember to use the chat. Post your questions there. I will collect this, and then I will pass any questions or feedback to Gianluca. Thanks, Gianluca, for being here. Gianluca is a computational designer, building engineer, and architect, now based in Dubai, serving as lead computational engineer at Sutari Middle East. And Gianluca has a strong foundation in computational design and expertise in tools like Rhino, Grasshopper, C#, etc. Before, Gianluca studied at the University of Bologna, and he has been working also at high-profile firms like Arup, Jacobs Engineering, Maffels Engineering, always showcasing his passion for geometry, math, and advanced mechanical systems. Welcome, Gianluca. Thanks for being here. And we are ready to see and learn more about Flow.
Perfect. Thank you, Carlos. And also thank to McNeil team to make this happen, make this webinar happen. And also thank to all the joiners. It's nice to see so many people interested in the plugin. So I will quickly share the screen. Okay. So Carlos, can you see my screen?
Yes, perfect.
Perfect. So I will have like a 15-20 minutes presentation about Flow, its features, capabilities. Then we will have a 15-20 minutes Grasshopper demo where I will showcase some more advanced features, more in analysis and results. And then we will have this QA session if you have questions or queries. So what is Flow? Flow is a Grasshopper plugin. This means that it works in Rhino and Grasshopper environment. At the moment, we have two versions, one for Rhino 7 and one for Rhino 8. But keep in mind that the Rhino 8 version is slightly faster because it relies on more advanced features, more advanced Rhino common libraries, especially for the mesh creation for the environment. But yeah, and it can also be used in Revit through Rhino inside Revit, because you have the possibility to have the full Revit model and just import in Rhino through Rhino inside the geometries that you need to build the model, like, for example, floors, walls, obstacles. And then if you turn on the Rhino previews into Revit, you are able to see the agent movement in the Revit model. So yeah, Flow has two different solvers, one for evacuations, one for crowd. I call it crowd solver. That is more like for routines simulations. Then it offers like a visual feedback of the movements in the Rhino viewport. But you can also record the simulation. I'm not talking about video recording, but I'm talking about data recording. So after this recording, you can again open the recording and analyze the data. And then it also provides analysis tools or more advanced, analysis like utilization, visibility, flow rate, and occupation of the floor. So Flow is based on a multi-agent system mechanism. This means that each agent, each person in the simulation is a standalone entity which takes decision based on this feedback loop between agent and environment. With environment, I mean all like the parameters which can be constructed in Flow, like gates, obstacles, neighbors, waiting areas, waiting points. And in each iteration, the agent has some feedbacks from this environment and can react based on these feedbacks. The agent is specified by a position, which is a point 3D in the Rhino environment, vector 3D, which is velocity, vector is direction in the environment. Then we have a desired velocity, which is another vector 3D. This desired velocity is basically the direction where the agent would like to go. And this direction is like aggregated with the main velocity with a steering vector. And then we have a separation boundary, which is used for neighboring separation. And then we have a cone of vision, which is used in the analysis components. So this is pretty much how you set up your model in Flow. You have the environment parameters, which basically are all the basic components that you use to set up the model. Then you have this component, which is assemble model, create model, where basically all the parameters come together and the model is computed. Then we have the solver, where basically the movement happen, the real calculation happen. Then if you reset the simulation, you are not able to, you basically will lose all your simulation. So there is the possibility to record, save the recording, then read the recording and visualize the results. This is an overview of the two solvers that Flow has. There is an evacuation solver and a crowd solver. And they are based on two different approaches. The crowd solver is based on a pathfinding algorithm that it is responsible to basically find the path that connects two or multiple points in a graph. I will zoom in so I can show you what the graph is. Basically, when you create a floor, in Flow, you input the boundary curves. Then Flow is responsible of creating the mesh, and this mesh has some edges, and these edges are basically the environment for the pathfinding algorithm. Different approach is used in the evacuation solver. That's because, unfortunately, Flow relies on CPU power, and this algorithm is quite, computational demanding. And just imagine to have, for example, from 5,000 to 10,000 people, and you want to simulate the evacuation, you will have like, and this obviously these paths are computed for each agent. And yeah, it's basically very, very computational demanding. So what I decided to do is use this flow field, which is basically a field of vectors. These vectors are guided by the boundary directions of the curves in Rhino, and also the boundary direction of the obstacles. So for example, as you see in this area, even if this is only one segment, but this has two different directions. This is because the segment has been split in Rhino, and two different directions have been assigned on each of them. I decided to go with this approach because usually in evacuation you have mainly a predefined path to follow. So this really helps in the computation because the agent need only to read the environment and apply the vector on the velocity. Yes. So I will first talk about the evacuation solver. So what you see here is an evacuation scenario with just a simple floor and one exit. Here, as you see, the agents follow the flow field on the floor, and the position of the agents are predefined. So this means that with this component, which is the create agent component, I can input the positions as point 3D. And I can input a label or tag, which basically says to the agents which floor they belong to. Then we also have other input, which are optional. We have the direction, which as default is random. We have the speed. Let's say that, for example, you have a group of agents with multiple ages, multiple mobilities. So you can here specify the speed of each of them. Then we have the reaction time. So let's say, for example, that you are on multiple floors and you want to assign different reaction times according to the position. Then you have this other tag to exclude, which basically says to the agent, okay, don't go in a specific area or in a specific floor. And then we have the color if you want to differentiate a group of agents. This is another example with multiple floors. It's pretty similar to the previous one. The difference is that we have this vertical connection, which is the stair, which is specified by entrance point, exit point, and path of the direction, which is a polyline. In this case, it's a simple line, but if you have more complex stair, obviously you have to use a polyline. There is also the possibility to introduce obstacles. You see here, if I zoom in a bit, that the flow field is influenced also by the obstacle segments direction. So before create the obstacle, I need to take care to set the directions of each of the curves and then create the obstacles. And then the flow field will be influenced by these directions. This is a more complex example, which involves multiple rooms. These multiple rooms are basically created using walls as obstacles. And as you can see also in this case, if I show you the flow field, you see that basically the model has been set up in such a way that the agents are guided to the preferred exit. So here you see in the bottom, we have 3 different exits, and the direction of the curves of the obstacles guide the agents towards the chosen exit. So I have also the possibility to play a bit with the field and decide where the agent should go during the simulation. This is another example. Here is showcased a stadium tribune. In this case, it's a more complex setup because we have basically to set for each step of the tribune a single floor. So basically they are all separated floors and they are connected to a vertical connection with different entrance points. So, and so you have also the possibility to use one single stair to connect multiple floors. Just imagine, for example, you are in you have a typical floor plan which replicates multiple times. You can just use a unique staircase and multiple entrance points, and the agent will merge inside the stair. Yeah, so I will also talk a bit about crowd solver. So the crowd solver, as I said, is a different approach. So instead of predefined the agent's positions, we have the sources. So each source is basically is specified by a point 3D. And if I set an interval in time, every time I overcome this interval in time, a new agent will be created. I have the possibility to set a starting time, end time, a cap if I want to stop the generation on a certain number of agents. And then we have these two inputs which go together, which are combinations and weights. In this example, we have only one parameter, which is the gate one. So here, as combination, I set gate one as weight 100. This basically is the probability that the agent will go towards that specific parameter. In the second example, we have different combinations because we have different levels of combinations. So we have the first level, gate one, gate two, second level, gate one, waiting area one, waiting area two, and third level, stair one. So when I set the combinations, basically, I say in the first level, we have gate one, gate two, and I assign to each of them the probability that the agent will go either towards gate one or gate two. But I can also, assign 80-20, for example. It's not like compulsory to set 50-50. Then we have waiting area one, waiting area two. So two combinations, two weights. And then we have only stair one. And we have 100% of weight. In this case, you see some command and some semicolon. When you use the command when you want to separate combination goals in the same level, and you use semicolon when you want to separate levels of combinations. This example showcases how a gate works. So the gate basically is specified by an entrance path, branches, exit paths, and boundary. So basically, agents approach the entrance through the entrance path. Then if the branches are occupied, they stop on the red point, which is basically the intersection between branches and entrance. And then after the waiting time, which basically they wait on the white point, they are free to move, free to go towards the exit path. In general, you can have like multiple branches. You can have starting from one branch to even 100 branches. There is no limitation. Then we have another parameter, which is the waiting area. That can be of two types, direct and full capacity. Direct means that the agent starts inside the area. When the agent is inside, the waiting time, which I can set here on the left, starts counting. And when the time is finished, the agent is free to go. The full capacity instead, there is a new input here, which is maximum capacity. And the time will start only if the maximum capacity is reached. So now, for example, when the five agents will be inside the waiting area, the time will start. And after 10 seconds, the agents will be free to go. These are basically two different parameters that you can use, for example, in the full capacity for meetings, for example. And you can use the direct approach to simulate, for example, restroom behavior. If I want, obviously, to simulate, I'm simulating like a stadium scenario where I have breaks during the game, so people go to the restroom. And this is quite, suitable for this case. And then we have the waiting point parameter, which is very simple. You just have a point, waiting time, the agent approaches the point, stops on it for, waits the time, and then is free to go. Also in the crowd model, we have the stair, which is specified also in this case by entrance point, exit point, polyline. But you can also have multiple path, multiple direction. So the stair can be bidirectional. So, but in this case, you can use the same mesh for the stair, but what you have to do is just use two curves for the input and also two different labels for the input. Yeah. So yeah, I will now dive into the grasshopper demo.
Very nice. Maybe one question
Yeah.
before you continue, but really cool. I'm always amazed how many different things you can do in grasshopper. I mean, I couldn't believe this years ago.
Yes. Yeah, exactly.
Well, there is Mason Brewer, and he asks, what if different types of entities need to use different paths? Can they have different flow fields?
What if different
So
kind of entities?
I guess different
So,
groups of persons
yeah.
that need to use different paths, if they can have different flow fields.
Yes. So you have the possibility to set counterflow behavior. So this means that each group of agent has, but we will see later also better in the Grasshopper demo, but basically each group of agent has a label, and the label that you assign is the same label that you assign for the floor and for the flow field. And you have some label to exclude. So if you want that some agent follow specific flow field and some agents don't, you just have to play a bit with the labels and say, okay, you don't go here and you go here. That's very, very, very simple. But in general, especially during evacuations, it's quite unlucky that you have different different flows for two different groups of people. I mean, yeah, you have different flows, but usually they don't intersect with each other.
Okay.
But for example, in the crowd solver, there is no problem. Here in the crowd solver, you can just, even if the flows are intersecting with each other, they just use a separation behavior and they can overcome the collision. Yeah.
Cool. Maybe later, if Mason wants to know more, he can reformulate his question, or after your demo, maybe it will be more clear. And yeah, one more question, and then please continue. From James Stewart, he asks, what kind of algorithm drives your crowd solver movement, e.g. social forces?
So the specific algorithm that I use is the A star. So
A star.
A star, yes. So it's basically it looks for the shortest path between two or multiple points.
Okay.
Yeah.
Cool. Thanks.
Okay, I will dive into Grasshopper. So I will open first this model, which is the one that you have seen before. So, so first of all, I want to show you how the Grasshopper tab works. We have here, the first tab is for the agents. So you can create agents, agent properties, basically deconstruct the agents in his basic parameters. Environment, to create all the environmental parameters. You have the model, create evacuation model, create crowd model, solver, evacuation solver, crowd solver, recording tools, util, which you have components for analysis. And then you have just a tab for the parameters and the license components. So as I said before, the solver takes as input two different parameters, the agents and the evacuation model. This evacuation model can be generated, the minimum input that you can use are the floor and the exit and the flow field. So actually the obstacles are optional as per the stair. So, and yeah, then the flow field is also created by a floor parameter, exit, and a label. So we'll now show the preview of the flow field. As you can see, the flow field directions are guided by the floor curves and the obstacles curves. For example, now I will try to disconnect the obstacles. And you will see that the flow field changes. This is because now it's only affected by the floor boundaries directions. I will now reconnect again the obstacles. Yeah. So once you have like created the model, I will just now focus more on the more advanced tool for the analysis. But basically, once you construct the model and once you construct your agents, you are ready to simulate. So this is the solver, which has some Boolean buttons. There's a reset button if you want to reset the simulation, a go button if you want to run the simulation, show agents. Yeah, I will turn on the preview now. This show agents, which basically turn on and off the preview of the agents, record button, and show legend button, which basically shows in the Rhino viewport some informations like agents count and speed and time. So usually when I run the simulation, I press go. So now you see the agents start to move. And if I press again go, they stop. And you see here in the output, they have, I have a list of agents, and all these agents are, all the positions of these agents are basically the positions which correspond to the specific time when I stop the simulation. Then here we have as input also floors and floor recording. But if I deconstruct this recording, you see that is basically empty. This is because I didn't press the record button. So now if I reset, I press record and I go again. Now you see this component is red because the recording now is null, because the recording is not be recorded yet. But let's say that now I'm satisfied with the simulation. I just have to press go again. And as you can see here, I have a flow recording. I can deconstruct the recording. But if I press reset again, I will lose my recording. So what I have to do is save the recording, this component. So we can do a quick test now. So I will create on my desktop a new folder. So let's say test. I have to input the path. I have to input the name. And the recording. Now I'm ready to save. Now, if I go back in the folder, you will see a CSV file. This CSV file contains basically all the simulation informations, the time, X, Y, Z of the positions, X, Y, Z of the velocity, ID, and colors. So you are free also to use this recording, this CSV file as you wish. I mean, you don't have to, again, use Flow to reconstruct the recording, but if you want just to take specific data, you can just use the CSV file. So now I can reset because I have saved my recording. And with this other component, read recording, I can input the path. So this is the folder. And I can, again, read the recording. So here I have, again, a flow recording, which I can deconstruct. And if we look at the structure of the output, we have here the positions. And the positions basically are in a data tree structure where each branch is, or better, is each part of the branch is the ID of the agent. And inside each path, you have the recorded positions. So each iteration, the position of the agent is recorded in this data tree. You see here that this has 51, for example, and this has 124 recording. This is why these 14 ID agent reached an exit before the others. So his position is not recorded anymore. You also have velocities, time, and colors. But here I have already a full recording of this simulation. So let's delete this, or I will just disable, and I will read this one. So again, I can deconstruct the recording. Yeah, so this is the full simulation of this specific scenario. What can I also do? If I go in the recording tab, I have two other components, extract simulation frame and play recording. I will take both of them. So let's start with the extract simulation frame. So I connect the recording and the input is asking for a simulation time. So from the time I check which is the maximum time of the simulation, which is from 0 to 56 seconds. So I create here a slider from 0 to 56. And I will turn off this preview. And now I can extract from this component a specific moment in time of the simulation. Then we have this other component, which is the play recording. Also, this one is asking for a recording. And instead of asking for the time, it asks for a speed, which is not a real life speed, but is more a scale factor of the simulation. So if I play now this one, you will see that the agents move very, very fast. That's because the operations that this component has to compute are much lower than the solver itself, because this one has only to read and apply. But I can modify the speed, so I can scale it. So if I play it now, I can also play with the speed of the simulation. And so this is pretty handy if you want to just simulate, also if you want to create a visualization, for example. Now I will switch to utilities. So here in utilities, you have utilization, visibility, checkpoints, evaluate section, and follow agent. I will start with the checkpoints component. So this component, if you input a recording and you input a list of points, so I will just, reference some points here. Let's say, for example, this one and this one. This component is basically computing the time, the average of all the time of all the agents that go through these 2 points. And so basically 27.8 seconds is the time that takes from all the agents that go through this point to go from start to end. But I can also input multiple points. So for example, I can input like 1, 2, and 3. So in this case, I will have 2 different values, one for the first 2 points and the other for the second and third point. Let's go back to 2, 1, and 2. If I switch to all agents, I can see the times for each of the agents that go through these 2 points. So I have only 2 data. This means that there are only 2 agents that go through these 2 points. And if I want to see which agents they are, I can remember that I have here the component deconstruct recording. So I can just, with the native grasshopper component, I can take the same branches, because remember that these paths are basically the ID of the agents. So I can take these paths to extract these positions. And I can also, play a bit with this point and see how the time changes and the agent's path changes. So yeah. Second component that I want to show you is the evaluate section. Here, you can also input, I will turn off these previews. So here you can input a recording and a section curve. I will take, for example, this one as section curve. Can input a curve, and this component will give you the flow rate in the specific section. So agent per second and agent per minute. So this means that through this curve are passing through 0.74 agent per second. So this is pretty, handy if you want to design openings and you have to respect some guidelines, for example. So then there is this component, which is follow agent, which is pretty funny. I really like it. So what this component does is, if you, for example, let's take these agents from extract simulation frame. I will take only one of them with a list item. Turn off. Yes. So we have this guy here, and we connect it to the follow agent component. We place a Boolean button. If I press through, the Rhino viewport will orient according to, the agent position and agent velocity. So this is actually not very suitable for evacuations, but is more suitable for crowd modeling, because during evacuation usually agents bump with each other, so it's pretty chaotic. So you are not able to see very nice. But just imagine that you have a full model in Rhino with nice materials in render view. And then you can actually check how the people experience your design, right? So let's say, for example, that you are designing a stadium and you have standard seats, VIP areas. With this component, you can check how a standard or a VIP experience is in your design, or if people bump in each other, and different things. And then we have the two main components, which is the utilization and the visibility component. I will start with the utilization component. Here, you have to input a recording. And in this case, evacuation model, but you can change here also crowd. So this is only one component, both for crowd and evacuation. So if you choose evacuation, you see this input will change in evacuation model. So I pick my evacuation model, which is here, and I input here. So if I turn off the floor, I get basically an heat map of the utilization of the floor. I have the possibility to show a legend. So basically, in the red areas, so this utilization component just computes how many agents go through a specific area. So this means that this corridor here is the most used in the entire floor, okay? And precisely 29 agents went through this corridor. And you have the possibility to also pick a specific region. So let's say that you want to check only the utilization of this area, okay? Which is not very, clear. If you have, for example, all light blue or white areas, you can pick a polyline, reference this polyline into grasshopper and just connect it here. So you will have a more clear, visualization of what's happening there. And then you have the possibility also to, if you switch utilization mode from total to time frame, you can pick a specific time. And we can even use the time that come from the play recording component. So if I input this time here and I play the simulation, so basically, just 1 second, I need to reset. So what happened is that the utilization just updates according to the agent movement, okay? So I have this real-time feedback between movements and utilization. Okay, I will switch now to the visibility component. With this component, basically you can check the visibility data on pretty much all the geometries. So how it works, you have, I will turn off the walls. I will turn on the floor. So this component is asking for a recording. Visibility settings that you can find in the same tab. Here, you have to input BREPs, but these BREPs, I mean, I've written here walls, but can really be anything, can be floors, can be, obstacles. Now I will input these walls here. I want to check the visibility. Oops, sorry. I think I mistakenly connected these to the label. Okay, we did it, sorry. Okay, so I have the walls. I want to check the visibility here, and I connect it to the BREP input. And then I have another input, which is the visibility range that I will keep 25 meters at the moment. I connect this to the visibility settings input, and I will turn off this preview. So here, what I have is like an heat map, which showcases the visibility data. I will turn off the utilization legend. I will turn on the visibility legend. So this legend is expressed in seconds. And this means that, for example, in this area, so this area has been seen for 236 seconds. This is because even though the simulation is 50 seconds, but each agent contributes to the total. So in the end, this area has been seen to 236 seconds. And also here, I can switch to time frame, and I can really input time. So, for example, yeah, so I can scroll this and see how the visibility changes according to the simulation. I will switch again to total because I want to show you how this visibility range affects the visibility. So let's say, for example, that you have something that needs to be seen very, very close. So like an advertisement that can be read only from 5 meters. So here you can input the meters. which is 5. And then you see how the heat map changes, because this area are the ones which are, which are seen from 5 meters. So yeah, you can also play with this value according to your design, design input. Here I also have a C# component with some code inside. I just want to show you what's happening inside here. So let's take maybe the same agent we took for the follow agent. Okay, so I have this guy here. So I can, with agent properties, I can deconstruct the agent in his point and velocity. I will input now the point here, and this one's here. You will see that it has basically a cone of vision, right? Better say that there's like some rays that approximate a cone of vision, and these rays, they basically intersect with the walls, okay, or whatever geometry you put inside. So they will register an intersection event, and they will, aggregated in order to get back the expression in seconds. So that's how this component works. So let's imagine, for example, that you don't want to do it on only one, but you want to do it in all of them. So this is actually what happened inside. So during the simulation, all the agents just start to intersect, the cone of vision starts to intersect with the walls, and the heat map that you see is just the final result of these intersections. Okay, I will just go quickly because I don't think we don't have much time. I will go quickly to another example, which is a crowd solver example. So yeah, so this is like a real case scenario. We have here an airport setup with six sources, which basically are these 6 entrances. We have some waiting points here as first level goal. We have some gates, which in this case are security checks. Then we have some stairs, and we have exits, okay? So also in this case, the setup is pretty much the same. The only difference is that you don't input the agents into the solver, but the agents come from the sources, which are here. Here you see I have 6 sources, which are basically all the 6 entrances. And each source has combinations, which basically these combinations are the labels that I insert in the basic parameters, which I create in Grasshopper. So based on this label, I can create combinations. As I explained before, common if it's same level, semicolon if it's different level, and weights, okay? And once the model is set up, I can simulate it. So yeah. Now you see that goes very, very slow because, the computation is not slow, it's slow the speed. That's because the model is very, very big. From this point, the entrance to this point is, I think, 50 meters. So, but you have the option to record it. And here, for example, I have already a recording, and you can play it. So let's do play recording. Let me turn off this. Yeah, and you can also increase, the speed. And yeah, also in this case, you have the possibility, I will not show you now how it works because I showed you before, but usually also you have the possibility to check utilization, visibility, all the things that we have seen before. Yeah, now I will switch very quickly to the presentation because I have some final slides to show you. So Flow is pretty new plugin for Grasshopper. It's been already 2 months that is in food4Rhino, and I really received a lot of feedbacks from users, customers. So first of all, I would like to thank all the customers for the trust in the product, and please give me feedbacks because at the moment the releases are in a time frame of, I would say, every week. So every week there is a new release with new features or improvements of existing features, right? But in general, these are basically this is the future roadmap that I would like to implement in Flow. We will have a real-time reaction to environmental conditions. So let's say, for example, that you have a stair or a path which is too crowded. With this behavior, the agent will be able to choose a different path or choose a different goal. For example, I can have waiting areas, one full waiting area, one free waiting area. So if one waiting area is full, the agent can, change his goal and go towards the empty one. So I think this will be very appreciated as in the future. And yeah, it's in the high priority schedule. Then we have also the elevators to be developed because, in general, if we are talking about transportation hub, airports, stations, elevators are really a very important elements in the circulation. So this will very soon be released in Flow. Crowd with preset agent positions, because at the moment in Crowd you can only use sources, but would be also nice to have some preset positions of the agents. And from that preset positions, I can then run the simulation. A bottlenecks component, because what you have seen is the utilization component, which doesn't take into account speed. But with these bottlenecks, we can actually showcase all the areas where there has been a slowdown in speed. So basically, all the slowest areas of the floor. And then we have different masses for agents. That's because if there are, for example, people with varying mobility abilities, we can set different mass. So this means that the other agents will be conditioned from the higher mass of the neighbor and will slow down. So the one with the bigger mass will dictate, the flow of the simulation. Yeah, this final slide, you can find more informations about Flow on the website, which is snhm.io, where you have also a contact us form. With this contact us form, you can give us feedbacks, you can give us feature requests, but also you can request a trial license. So if you visit our website, you will find different licensing options, including a trial license. So yeah, feel free to reach out and we will be happy to assist you. On the right, you can find other resources. So some YouTube videos, some tutorials on how to set up the models, evacuation and crowd solvers. Discord channel that basically has the same purpose of the contact us form. We use it for bugs in general, bug fixing, or feedback, or general feedback from users, or more advanced feature requests. And yeah, that's the link for food4Rhino, where you can download the plugin and test it. So this is pretty much all. Thank you for listening, and I would be happy to answer now some questions if you have some.
Brilliant. Many thanks. Very, very
Thanks.
cool
Thanks.
features. Yeah, actually, there are quite a few questions.
Yeah.
Let's start by order of appearance. Okay, Ines Pereira asks if the evacuation simulations are deterministic.
If deterministic, you mean that you preset directions? Yes. But said that, there are still some events that can, influence the simulations, like the neighboring interaction, for example. So it is true that the evacuation is predetermined in terms of flow patterns, but it's also true that, it depends on how the agents interact with the neighbors. So if they have like separations because they are too close with each other, this means if there is like a very, very tiny opening, how the crowd will react to this opening. So they will just, shrink with each other, they will push with each other. So there are still some behaviors which are not deterministic, but need to be simulated. But I would say that in general, the evacuation flow is already pre-designed, right? So it's true that there is a human factor in the simulation, but unfortunately, I don't think I mean, at the moment, I don't have the skills to use some, more advanced algorithm that can involve in artificial intelligence or machine learning to simulate these behaviors. So unfortunately, I need to stick on the just points and vectors operation.
Okay. Then James Stewart is the person that asked before what kind of algorithms drives your crowd solver movement. He now wants to rephrase his question a little. He says, I was hoping to understand the collision avoidance system you use when agents are following your paths, with either the crowd solver network or the flow field, since they look like they can avoid each other.
They can or they can't?
They can.
They can. Yeah. So basically, each agent has a separation boundary, right? So when most of the time, everything is in the flow is calculated according to distances. So when the distance between the agent and his neighbor is less than the separation radius, a new vector is generated, which pushes the agent far from the neighbor. Okay, and there is this behavior, and there is also a bias behavior. This means that if the agent like bump into a neighbor and they are in front of each other, but basically this bias will like dictate the agent to move towards the already existing direction. So it means that if the agent is slightly on the right compared to another one, this bias will reinforce the behavior. So the agent will just be pushed a bit more on the right, and the other one a bit more on his right, which is the agent left. So yeah, it would be better to explain it with visualization, but I hope it was clear.
Okay, thank you. One more question, this time from Karl Daubmann. Can you populate different rooms with different densities of people? This would illustrate different occupancies and uses related to US building codes.
Yes, so everything in Flow can be designed in Rhino or Grasshopper. So if you are able in Grasshopper to set up different boundaries, you are able also to populate different boundaries with different number of points. With, for example, populate geometry or populate boundary rectangle, you can, just populate with points and choose different, number of points. And then you can just use these as generating points for the agents. And you can even assign different speeds, different colors in order to differentiate them. So yeah, but you can also, use Rhino. So you can just input points in Rhino and reference them into Grasshopper, and then create the agents.
Okay. One Ines Pereira, he made the previous question. She says, what I meant by a deterministic is that if you feed your model the exact same inputs, will it always produce the output? For example, evacuation time?
Yes, if you start from the same positions, yes. What you can do is change, but even if you change the starting direction, it will, I would not say totally change, but it will like considerable change in terms of time. That's because the starting direction, so the starting velocity, it will be different from each sample, and this will bring to different results. But if you start with the same positions and same starting velocities, you will get the same results.
Thank you. And she also asks, how did you validate your tool? If you perform any real life experiments or do you just compare it with other tools?
So
I guess, well, you mentioned already about the algorithm you use it. I guess this has been.
No, yeah, in validation in general, I used actually for the evacuation, I used for the development 2 different guidelines. The first one is the International Maritime Organization, which basically gives some guidelines for, I would like to specify that these guidelines are not for example, fire safety evacuations, but are just for software simulation developments. Okay, so there are some tests that you have to perform in order to validate, in order to assess that your tool is able to simulate. That you can find in our website under the documentation tab. Unfortunately, I didn't find crowd or better routine validations. But I would say that you can maybe use third parties tools, which are for sure more consolidated than mine in order to validate the results. Or maybe you can just compare with real case scenarios if you have data about this. But in general, the validation is only for evacuation, not for crowd simulation.
Okay. One more question by James Stewart. Can different agents have different preferred movement speeds in the same simulation?
Can different agents have different preferred movements? If I understood correctly, you can basically set different goals in the source. So the movements of the agents is basically, they pretty much depend on which goals you give in the source component and how much will be the probability that the agent will pick a specific goal, basically. So you can have multiple sources, you can have multiple goals. So you definitely can have multiple movements for multiple agents. Yeah.
Perfect. What else? New question by Abanub Saed. Can we know what is the last regions that reach the gate so we can edit the design and create another gate for them?
Can you say it again, Carlos?
Yeah, can we know what is the last regions that reach the gate so we can edit the design and create another gate for them? I guess the last group of people that reach the gate, or last regions that reach the gate?
At the moment, there is not a specific component that does this, but for sure you can, record and play the recording, and you can extract a simulation frame and check visually, but also with data, because which is the last one. Yeah.
Okay. Another question by Silvia Romero. Could you please confirm that the data you have generated and saved in as CSV, if it contains in XYZ the XYZ information of each agent through all its movements.
Yes.
Okay.
So each agent register its position in XYZ coordinates in each instant of time. So basically, you have, I will reopen again, so maybe I can show it better. This was just a quick recording, like maybe 5 seconds recording. So basically here you see the ID. So if I go down, yeah, you see that the ID changes. So for each agent, I register for each iteration, the ID and the positions. So these are basically X, Y, Z coordinates of the position for each instant in time. So you see here, this time is growing and until it reaches, yeah, here there is the shift between 0 and 1. So until it reaches 8.2 seconds. So yeah, it's basically, it registers everything. And unfortunately, there is a limitation in terms of rows in the CSV file, which is, I think, 1 million. But if this limitation is reached, a new CSV file is created in the same folder.
Okay.
And then when you read the recording, basically just put them together. And yeah, that's it.
Perfect. Then Carl Taubman, this is more, I guess, a question about your licensing. Could we potentially ask for more than one seat with educational license? A floating license would work too. Envisioning this as a course assignment. Probably he asked if you have kind of the Rhino Lab license or multi-user license for educational purposes.
Yes, I was thinking about this actually because I got some requests about this license. I'm still thinking which one would be the best approach, but definitely in the near future, there will be a possibility to have educational pools where maybe students can learn from it. And yeah, that's for sure.
Okay, thanks.
But yeah, just one other thing. At the moment, if you buy an educational license, it will be locked to the specific machine. So it can be used only by one person, basically. Yeah.
Okay, one more by James Stewart. In your visibility mapping, can the cone of vision be customized to wider or narrower angles, representing different level of human focus, e.g. central, paracentral, near, mid, far, peripheral?
Yes. No, sorry, no, it cannot customize. It cannot be customized, but I was thinking to extract it from the component and make it customizable. But I would say that I have tested quite a lot of different radius, and the percentage of people that have limitation in visibility is very, very, low compared to the group, the total group. So the influence of these would not be reflected in the overall analysis. But yeah, that's for sure. That's a good point. For sure in the future I will extract the input in order to because at the moment the standard angle is 30 degrees per side. So total 60 degrees, which is the standard visibility cone angle. But yeah, in the near future, it will be externalized. Yeah.
Cool. Also, very nice feedback and congratulations from many users. One is Domenico Casalnuova, is your brother?
Yes, my
Okay,
brother.
he
Yes.
says
Thank you.
brilliant, genius. But well, also thanks a lot from Guillermo Perdomo. Amazing. Thank you very much, Maria Georgieva. Fantastic. Our firm will definitely want to use this plugin for modeling alternative solutions from Jordan Yerburi. Incredible, says Santiago Matias Cabrejo. I miss Pet Pro, and this is not just a replacement, but an improvement in many, many levels. Really amazing, but I'm a noob Sanet. Okay, lots of nice feedbacks. And I will finish with some other questions, okay? Because we ran already out of time. Again,
Okay.
if anyone, this is being recorded, and I will upload the webinar with all the questions to our food4Rhino YouTube channel during today and tomorrow. But let's answer a few more questions. Assuming this is my Maston Lions, assuming you are using PRNG to ensure randomness between model runs, are we able to set the RNG seed ourselves?
Are we able to set, sorry, Carlos?
The RNG seed ourselves, assuming you are using PRNG.
Not sure I got the
The
question.
seed, I mean, if you can change the seed of
Yes.
the.
Yes, sure. Yeah. You can, I mean, you cannot do it into the with Flow, but you can do it in like native Grasshopper components. So you have the possibility to generate random points, but also random velocities, which basically is the same thing. So point 3D, vector 3D have three X, Y, Z coordinates. So you can generate random vectors and changing the seed, and you can input these into the velocity input when you create the agents. Yeah.
Cool.
Yeah.
Then this is a suggestion by Silvia Romero. She says that a potential future capability could be the assignment of specific tasks for each of the agents before exiting. This could be used in case of some persons have to undertake specific activities before exit. And thank you for the interesting presentation. This is a suggestion. Maybe there are some people that need to, I don't know, wait until the end or.
Yeah, that's a good point. Yeah, for sure.
And the very last question by Jordan Yerburi. Can the simulations be used to determine agent behaviors other than evacuation? For example, can we determine how products placed on store shelves impact consumer choices for making purchases in a store?
I mean, as long as you are able to, I would say, translate the data that you get from the analysis into your specific application, I would say why not? Like, I mean, Flow has been designed for evacuation and crowd simulation, right? But then if you can take data which, like, for example, flow rates, utilization, how many people go in a specific areas, how much time takes to go from a specific point to another, then you can use this data as you wish. And yeah, you can even apply it, for example, for environmental analysis or for structural analysis to have just a qualitative assessment of the weight that you will have in a specific area. Yeah.
Okay, many thanks. That was the last question. And yeah, thank you. It was an interesting plugin by Jerusalem Tibete, and cheers from many other users. Thank you very much, Gianluca. It was a pleasure. Again,
thank you all. Thank
I
you
will
again all for
upload the video, the recorded session during today and tomorrow to food4Rhino webinars YouTube channel, and hope to meet you soon. Hope it goes everything well in Dubai.
Yes.
Now it's
the
nice season,
nice
right?
weather. Yes.
Nice weather.
Yes, exactly.
And yeah, to the audience also, many thanks for being here one more time with us at this food4Rhino webinar series. Cheers.
Thank
Bye.
you all. Thank you. Bye all.